Big O notation is a mathematical tool used by computer scientists to find the upper bound, or worst-case scenario, of an algorithm's growth. It determines the theoretical maximum amount of time or space a program will require to process data as that data scales toward infinity. To see why this matters, imagine running the exact same program on a modern multi-million-dollar supercomputer and a 10-year-old consumer laptop. Naturally, the supercomputer finishes the task first, but the supercomputer didn't win because it was running a superior algorithm. It won because it applied raw processing power to brute force its way through the work, masking any underlying inefficiencies in the code. This hardware discrepancy creates a serious problem for software developers. Because clock speed varies wildly from machine to machine, programmers need a pure mathematical way to measure efficiency based on the actual operations the code performs, independent of the hardware running it. Big O provides exactly that universal measurement. It allows engineers to mathematically predict if a program will survive being scaled up to massive real-world datasets before they ever hit the run button. Big O notation measures efficiency across two dimensions: time complexity, which tracks the number of steps an algorithm takes to complete a task, and space complexity, which measures how much memory it allocates while running. Calculating this begins with a highly practical first step: looking directly at a block of code and counting its primary operations. Looking at this textbook snippet, we see a simple method designed to calculate a percentage. If we follow the instructions to count the operations, we see exactly two fixed math steps: dividing x by y and multiplying by 100. Because those two math operations only execute once per function call, regardless of whether the input numbers are tens or trillions, the algorithm's efficiency is constant. In Big O notation, this is written as O of 1. Compare that constant operation to a standard conditional loop searching through a list. If that list has n items, the algorithm is forced to repeat its check n times. The time complexity scales in direct proportion to the size of the data. Isolating these core operations and linking them to n, a variable representing the size of the dataset being processed, forms the primary foundation of calculating efficiency. Once the operations are mapped to n, we apply the second major rule of Big O calculation: drop the constants and lower order terms. If a function requires n plus 25 steps to execute, or even exactly 2 times n steps, Big O ignores the 25 and the multiplier. Both are simply categorized as O of n. When an application scales to process millions or billions of data points, a static addition of 25 steps becomes mathematically irrelevant. Only the largest exponent, or the dominant term, dictates the actual shape of the growth curve. This chart illustrates how these dominant terms stack up against each other, with the number of operations on the y-axis and the size of the data on the x-axis. We see our O of 1 constant efficiency as a perfectly flat line. Our O of n linear algorithm climbs at a steady diagonal. Right in between them sits O log n. This represents logarithmic efficiency. Algorithms like binary search trees fall here because they eliminate half the remaining data with every single step, making them highly efficient for massive datasets. On the other side of the scale, we find quadratic algorithms, like nested loops or bubble sorts. Categorized as O of n squared, these become incredibly slow and resource-heavy as data grows. Finally, there are brute force algorithms that trigger exponential or factorial growth. These scale so poorly they can crash a system processing even a surprisingly small amount of data. By stripping away the static constants and plotting out the dominant mathematical terms, a developer can look at a few lines of logic and accurately predict exactly when the code will break under pressure. Armed with Big O notation, a programmer can theoretically predict how a specific architecture will behave under stress before it is even compiled. They can identify the scaling limits of an application simply by reading its logic. Looking at the hierarchy graph, it might seem like the goal is to write flat, O of 1 constant functions for everything, but algorithm design is entirely dictated by the context of the problem being solved. If an engineer is building a real-time financial trading platform or managing extreme server loads, they have to ruthlessly optimize for constant or logarithmic efficiency to save every available millisecond. Conversely, if a developer is organizing a strictly limited dataset, say 50 internal user accounts, a theoretically slow quadratic sort might be the most appropriate choice. It takes far less time to write, and on a dataset that small, it still executes in a fraction of a second. Big O notation provides a mathematical framework for evaluating these trade-offs. It ensures developers choose the right solution for the required scale, matching the complexity of the code to the specific needs of the problem.